Welcome to Hitchhikers TV. Welcome to Grade 10 Science Most Essential Learning Competency 3 for Week 5 to 6 of the first quarter lesson. Let's study and explain the different processes that occur along the plate boundaries. This presentation would enable Grade 10 students to answer what geologic features and events form at plate tectonic boundaries.
Yeah, boy!
Copyright disclaimer under Section 107 of the Copyright Act 1976. Allowance is made for fair use for purposes such as criticism, commenting, news reporting, teaching, scholarship, and research. Fair use is a use permitted by copyright statute that might otherwise be infringing. Non-profit, educational, or personal use tips the balance in favor of fair use. This is for educational or teaching purposes. Come along and explore with Hitchhikers TV. Let's learn about plate tectonics theory as we continue to study Earth and space. Remember that Earth and space science explores the interconnections between the land, ocean, atmosphere, and life of our planet. These include the cycles of water, carbon, rock, and other materials that continuously shape, influence, and sustain Earth and its inhabitants. In some ways, Earth resembles a giant jigsaw puzzle. That is because its outer surface is composed of about 20 tectonic plates, enormous sections of Earth's crust that roughly fit together and meet at places called plate boundaries. Plate boundaries are important because they are often associated with earthquakes and volcanoes. When Earth's tectonic plates grind past one another, enormous amounts of energy can be released in the form of earthquakes. Volcanoes are also often found near plate boundaries because molten rock from deep within Earth called magma can travel upward at these intersections between plates. In the plate tectonics and supercontinent cycles, the present continents were once all part of a supercontinent that Alfred Wegener named Pangaea, all land. More recent studies of continental matchups and the magnetic ages of ocean floor rocks have enabled us to reconstruct the history of the breakup of Pangaea. Pangaea was not the first supercontinent. It was preceded by Pangaea, 600 to 540 million years ago, Rodinia, 1,100 to 750 million years ago, and by others before that. In fact, in 1966, Tuzo Wilson proposed that supercontinents are part of an ongoing cycle, which we now refer to as a Wilson cycle. In a Wilson cycle, continents break up, and fragments drift apart only to collide again and make a new continent. At present we are in the stages of a Wilson cycle where fragments are drifting and changing their configuration. North and South America, Europe, and Africa are moving with their respective portions of the Atlantic Ocean. The eastern margins of North and South America and the western margins of Europe and Africa are called passive margins because there is no subduction taking place along them. Because the oceanic crust formed by spreading along the mid-Atlantic ridge is not currently being subducted, except in the Caribbean, the Atlantic Ocean is slowly getting bigger, and the Pacific Ocean is getting smaller. This situation may not continue for too much longer, however. As the Atlantic Ocean floor gets weighed down around its margins by great thickness of continental sediments, it will be pushed farther and farther into the mantle, and eventually the oceanic lithosphere may break away from the continental lithosphere and begin to subduct. A subduction zone will develop, and the oceanic plate will begin to descend under the continent. Once this happens, the continents will no longer continue to move apart because the spreading at the mid-Atlantic ridge will be taken up by subduction. If spreading along the mid-Atlantic ridge continues to be slower than spreading within the Pacific Ocean, the Atlantic Ocean will start to close up, and eventually, in a 100 million years or more, North and South America will collide again with Europe and Africa. If this continues without changing for another few 100 million years, we will be back to where we started, with one supercontinent. Pangaea began to rift apart along a line between Africa and Asia and between North America and South America at around 200 million years ago. During the same period, the Atlantic Ocean began to open up between northern Africa and North America, and India broke away from Antarctica. Between 200 and 150 million years ago, rifting started between South America and Africa and between North America and Europe, and India moved north toward Asia. By 80 million years ago, Africa had separated from South America, and most of Europe had separated from North America. By 50 million years ago, Australia had separated from Antarctica, and shortly after that, India collided with Asia. The ideas of continental drift and seafloor spreading became widely accepted by 1965, and more geologists started thinking in these terms. By the end of 1967, Earth's surface had been mapped into a series of plates. The major plates are Eurasian, Pacific, Indian, Australian, North American, South American, African, and Antarctic plates. There are also numerous small plates, e.g., Juan de Fuca, Nazca, Scotia, Philippine, Caribbean, and many very small plates or subplates. The Juan de Fuca plate is actually three separate plates, Gorda, Juan de Fuca, and Explorer, all moving in the same general direction but at slightly different rates. Within the past few million years, rifting has occurred in the Gulf of Aden and the Red Sea, and also within the Gulf of California. Incipient rifting has begun along the Great Rift Valley of eastern Africa, extending from Ethiopia and Djibouti on the Gulf of Aden, Red Sea, all the way south to Malawi. The fact that plates include both crustal material and lithospheric mantle material makes it possible for a single plate to include both oceanic and continental crust. The North American plate includes most of North America, plus half of the northern Atlantic Ocean. Similarly, the South American plate extends across the western part of the southern Atlantic Ocean, while the European and African plates each include part of the eastern Atlantic Ocean. The Pacific plate is almost entirely oceanic, but it does include the part of California west of the San Andreas Fault. There is strong evidence around the margins of the Atlantic Ocean that this process has taken place before. There are roots of ancient mountain belts along the eastern margin of North America, the western margin of Europe, and the northwestern margin of Africa, which show that these land masses once collided with each other to form a mountain chain. The mountain chain might have been as big as the Himalayas. Plates move as rigid bodies, so it may seem surprising that the North American plate can be moving at different rates in different places. The explanation is that plates rotate as they move. The North American plate, for example, rotates counterclockwise, while the Eurasian plate rotates clockwise. Plate motions can be tracked using Global Positioning System, GPS, data from different locations on Earth's surface. Rates of motions of the major plates range from less than 1 cm/y to more than 10 cm/y. The Pacific plate is the fastest, moving at more than 10 cm/y in some areas, followed by the Australian and Nazca plates. The North American plate is one of the slowest, averaging 1 cm/y in the south up to almost 4 cm/y in the north. The apparent line of collision runs between Norway and Sweden, between Scotland and England, through Ireland, through Newfoundland and the Maritimes, through the northeastern and eastern states, and across the northern end of Florida. When rifting of Pangaea started at approximately 200 million years ago, the fissuring was along a different line from the line of the earlier collision. This is why some of the mountain chains formed during the earlier collision can be traced from Europe to North America and from Europe to Africa. It is probably no coincidence that the Atlantic Ocean rift may have occurred in approximately the same place during two separate events several hundred million years apart. The series of hot spots that has been identified in the Atlantic Ocean may also have existed for several hundred million years, and thus may have contributed to rifting in roughly the same place on at least two separate occasions. The Earth's outer crust, the lithosphere, is composed of a series of tectonic plates that move on a hot-flowing mantle layer called the asthenosphere. Heat within the asthenosphere creates convection currents that cause tectonic plates to move several centimeters per year relative to each other. When two tectonic plates meet, we get a plate boundary. There are three major types of plate boundaries, each associated with the formation of a variety of geologic features. Geologic events and features include the formations of deep ocean trenches, volcanoes, island arcs, submarine mountain ranges, and fault lines are examples of features that can form along plate tectonic boundaries. There are many different types of plate boundaries. For example, sections of Earth's crust can come together and collide, a convergent plate boundary, spread apart, a divergent plate boundary, or slide past one another, a transform plate boundary. Each of these types of plate boundaries is associated with different geological features. Boundaries between the plates are of three types: divergent, moving apart; convergent, moving together; and transform, moving side by side. The plates are made up of crust and lithospheric mantle. Even though the plates are in constant motion, and move in different directions, there is never a significant amount of space between them. Plates move along the lithosphere-asthenosphere boundary, because the asthenosphere is relatively weak. It deforms as the plates move, rather than locking them in place. If two tectonic plates collide, they form a convergent plate boundary. Usually, one of the converging plates will move beneath the other, a process known as subduction. Deep trenches are features often formed where tectonic plates are being subducted and earthquakes are common. As the sinking plate moves deeper into the mantle, fluids are released from the rock, causing the overlying mantle to partially melt. The new magma, molten rock, rises and may erupt violently to form volcanoes, often building arcs of islands along the convergent boundary. In convergent boundaries, the convergent plate boundaries occur, where two plates are moving toward each other, are of three types, depending on whether ocean or continental crust is present on either side of the boundary. The types are ocean-ocean, ocean-continent, and continent-continent. The newly produced magma, which is lighter than the surrounding mantle rocks, rises through the mantle and sometimes through the overlying oceanic crust to the ocean floor, where it creates a chain of volcanic islands known as an island arc. A mature island arc develops into a chain of relatively large islands, such as Japan or Indonesia, as more and more volcanic material is extruded and sedimentary rocks accumulate around the islands. The largest earthquakes occur near the surface, where the subducting plate is still cold and strong. As the subducting crust is heated and the pressure increases, water is released from within the subducting material. This water comes primarily from alteration of the minerals pyroxene and olivine to serpentine near the spreading ridge shortly after the rock's formation. The water mixes with the overlying mantle, which lowers the melting point of mantle rocks, causing magma to form. This process is called flux melting or fluid-induced melting. Typically, a convergent plate boundary such as the one between the Indian plate and the Eurasian plate forms towering mountain ranges, like the Himalaya, as Earth's crust is crumpled and pushed upward. In some cases, however, a convergent plate boundary can result in one tectonic plate diving underneath another. This process, called subduction, involves an older, denser tectonic plate being forced deep into the planet underneath a younger, less dense tectonic plate. When this process occurs in the ocean, ocean trench can form. These trenches are some of the deepest places in the ocean, and they are often the sites of strong earthquakes. Convergent boundary in the Philippines. The Philippine Sea Plate is tectonically unusual in that almost all the boundaries are convergent. The Pacific Plate is subducting beneath the Philippine Sea Plate to the east, while the west/northwestern part of the Philippine Sea Plate is subducting beneath the continental Eurasian Plate. When subduction occurs, a chain of volcanoes often develops near the convergent plate boundary. One such chain of volcanoes can be found on the western coast of the United States, spanning across the states of California, Oregon, and Washington. Examples of ocean-ocean convergent zones are subduction of the Pacific Plate south of Alaska, Aleutian Islands, and west of the Philippines, subduction of the Indian Plate south of Indonesia, and subduction of the Atlantic Plate beneath the Caribbean Plate. The ocean-continent convergent boundaries. At an ocean-continent convergent boundary, the oceanic plate is subducted beneath the continental plate in the same manner as at an ocean-ocean boundary. Rocks and sediment on the continental slope are thrust up into an accretionary wedge, and compression leads to faults forming within the continental plate. The mafic magma produced adjacent to the subduction zone rises to the base of the continental crust and leads to partial melting of the crustal rock. The resulting magma ascends through the crust, producing a mountain chain with many volcanoes. Examples of ocean-continent convergent boundaries are subduction of the Nazca Plate under South America, which has created the Andes Range, and subduction of the Juan de Fuca Plate under North America, creating the mountains Garibaldi, Baker, St. Helens, Rainier, Hood, and Shasta, collectively known as the Cascade Range. In the continent-continent convergent boundary, a continent-continent collision occurs when a continent or large island that has been moved along with subducting oceanic crust collides with another continent, figure 4.29. The colliding continental material will not be subducted because it is not dense enough, but the root of the oceanic plate will eventually break off and sink into the mantle. There is tremendous deformation of the pre-existing continental rocks, and creation of mountains from that rock, as well as from any sediments that had accumulated along the shores of both continental masses, and commonly also from some ocean crust and upper mantle material. Examples of continent-continent convergent boundaries are the collision of the India Plate with the Eurasian Plate, creating the Himalaya Mountains, and the collision of the African Plate with the Eurasian Plate, creating the series of ranges extending from the Alps in Europe to the Zagros Mountains in Iran. When a subduction zone is jammed shut by a continent-continent collision, plate tectonic stresses that are still present can sometimes cause a new subduction zone to develop outboard of the colliding plate. When two plates are moving away from each other, we call this a divergent plate boundary. Along these boundaries, magma rises from deep within the Earth and erupts to form new crust on the lithosphere. Most divergent plate boundaries are underwater and form submarine mountain ranges called oceanic spreading ridges. While the process of forming these mountain ranges is volcanic, volcanoes and earthquakes along oceanic spreading ridges are not as violent as they are at convergent plate boundaries. In divergent boundaries, the divergent plate boundaries are spreading boundaries, where new oceanic crust is created from magma derived from partial melting of the mantle. The partial melting happens when hot mantle rock is moved from deep within Earth where pressures are too high for it to be liquid, to shallower depths where the pressure is much lower. A divergent plate boundary often forms a mountain chain known as a ridge. This feature forms as magma escapes into the space between the spreading tectonic plates. One example of a ridge is the Mid-Atlantic Ridge, an undersea chain of mountains that formed as two pairs of tectonic plates spread apart, the North American Plate and the Eurasian Plate in the north, and the South American Plate and the African Plate in the south. Because ocean ridges are found underwater, often at great depths, they can be hard to study. In fact, scientists know more about the surfaces of some of the other planets in our solar system than they do about ocean ridges. At spreading centers, the lithospheric mantle is relatively thin. The upward convective motion of hot mantle material generates temperatures that are too high for the existence of a significant thickness of rigid lithosphere at the same time that the plates are falling away from each other. The triangular zone of partial melting near the ridge crest is approximately 60 kilometers thick and the proportion of magma is about 10% of the rock volume, thus producing crust that is about 6 kilometers thick once the melt escapes from the rock in which it formed, and ascends. Most divergent boundaries are located in the oceans, and the crustal material created at a spreading boundary is always oceanic in character. In other words, it is mafic igneous rock, basalt or gabbro, with minerals rich in iron and magnesium. Spreading rates vary considerably, from 1 cm/y to 3 cm/y in the Atlantic, to between 6 cm/y and 10 cm/y in the Pacific. Some of the processes taking place in this setting include melted rock, magma, from the mantle rising up to fill the voids left by divergence of the two plates. Pillow lavas forming where melted rock emerges on the ocean floor and is cooled by seawater, vertical sheeted dikes intruding into cracks resulting from the spreading, magma cooling more slowly in the lower part of the new crust, forming bodies of gabbro. Spreading is thought to start with lithosphere being warped upward into a dome by buoyant material from an underlying mantle plume or series of mantle plumes. The buoyancy of the mantle plume causes the dome to fracture in a radial pattern, with 3 arms spaced at approximately 120 degrees. The third type of plate boundary occurs where tectonic plates slide horizontally past each other. This is known as a transform plate boundary. As the plates rub against each other, huge stresses can cause portions of the rock to break, resulting in earthquakes. Places where these breaks occur are called faults. A well-known example of a transform plate boundary is the San Andreas Fault in California. When a series of mantle plumes exists beneath a large continent, the resulting rifts may align and lead to the formation of a rift valley, such as the present-day Great Rift Valley in eastern Africa. This type of valley may eventually develop into a linear sea, such as the present-day Red Sea, and finally into an ocean, such as the Atlantic. It is likely that as many as 20 mantle plumes, many of which still exist, were responsible for the initiation of the rifting of Pangaea along what is now the Mid-Atlantic Ridge. In transform fault boundaries. The transform fault boundaries exist where one plate slides past another without producing or destroying crust, except in the special case where the transform boundary has bends and jogs. There will be collisions and divergence on a small scale as the jogs crash into the bends, or open up small windows to deeper crust. Most transform faults connect segments of mid-ocean ridges and are thus ocean-ocean plate boundaries. Some transform faults connect continental parts of plates. An example is the San Andreas Fault, which connects the southern end of the Juan de Fuca Ridge with the northern end of the East Pacific Rise, a ridge, in the Gulf of California. The part of California west of the San Andreas Fault and all of Baja California are on the Pacific Plate. But transform faults do not just connect divergent boundaries. The Queen Charlotte Fault connects the north end of the Juan de Fuca Ridge, starting at the north end of Vancouver Island, to the Aleutian Subduction Zone. Volcanoes in an east-west zone across central Luzon may be associated with a leaky transform fault that connects the two subduction zones. The transform fault is offset to the right by the younger Philippine Fault. The volcanoes of the Philippines are the most deadly and costly in the world. The plate tectonics in the Philippines is complex and includes plate boundaries that are changing rapidly. Several microplates are getting squeezed between two convergent plate margins. Stratigraphic evidence indicates cessation and reactivation of subduction at some trenches. The currently active volcanoes in the Philippines define two north-south trending arcs. The scale and type of volcanism varies from monogenetic cinder cone fields to large stratovolcanoes and calderas. Composition of volcanic rocks range from tholeiitic basalt to andesite to shoshonite. Black triangles equals active subduction zones with teeth on the overriding plate, white triangles equals inactive subduction zones with teeth on the overriding plate, arrows equals transform or major strike-slip faults, red triangles equals volcanoes active in the last 10,000 years. Plates and microplates shown in different colors. Based on Divis, 1983. Volcanoes from Simkin and Siebert, 1994. In the west, more steeply east-dipping subduction of the Eurasian Plate, South China Sea Basin and the transitional oceanic continental crust of the Palawan Block, along the 560-mile, 900 kilometers, length of the Manila and Sulu Trenches produces a discontinuous line of active volcanoes from Taal in the south to Irea in the north. Volcanism associated with this subduction zone began about 10 million years ago. In the east, shallow west-dipping subduction of the Philippine Plate at the Philippine Trench produces a line of volcanoes from below in the south to Mayon in the north. Based on Divis, 1983. Volcanoes in an east-west zone across central Luzon may be associated with a leaky transform fault that connects the two subduction zones. The transformed fault is offset to the right by the younger Philippine Fault. Based on Divis, 1983. The volcanoes of the Philippines are the most deadly and costly in the world. Fatalities have been caused by 13% of the historic eruptions, most notably at Taal and Mayon, and 22% of the eruptions caused damage. Mudflows are more common in the Philippines, compared to other regions, because of heavy rains. Tsunami are more commonly associated with eruptions at the Philippines than in any other volcanic region. Many of the Holocene volcanoes in the Philippines have eruptive products that have not been dated. Since the Philippines Institute of Volcanology and Seismology has been established, the impacts of eruptions have been greatly reduced.